This presentation is delivered by the Stanford Center for Professional Development.
All right, let's get started. So today, video segment is Something happened. Okay, we have a little problem. I guess we can stop and start over if you would like. Yeah, let's go. Okay. Okay, my computer just crashed. Okay, let's start over. All right, take two. So today video segment is about polypod. Have you heard about polypod? No? So these are little small robots that we connect to build a shape, so that we call them reconfigurable robots. And they are modular, and there is a lot of interest in this area. And one of the pioneer in this area was Mark Im. Mark Im was a PhD student in the robotics lab in the early 90s, and he is now a professor teaching robotics and building very advanced polypod systems. So I'm going to show you the concept that he proposed in '94 and some of the realization he made at that time. Polypod. If we could have the light off, please.
Polypod is a reconfigurable modular robot. It's made up of two types of modules called segments and nodes. Segments are 2-degree freedom modules with 2 motors, force and position sensing, and a microcomputer on board. Nodes are rigid cube-shaped housings for batteries. Segments may be mounted parallel to each other, or they may be mounted perpendicular to each other. Modules may also attach on any face of a node. Simple locomotion gates are statically stable gates that move along a straight line. The rest of this video will quickly present a series of locomotion gates through simulation and implementation on Polypod. Each segment runs semi-autonomously by controlling each degree of freedom with a sequence of behaviors. All of the following motions use 2 simple behavioral modes called ends mode and springs mode. With the springs mode, a degree of freedom acts as a well-damped spring using force sensors. With ends mode, the degree of freedom moves at a constant speed until it reaches a joint limit. Many of the gates shown here are extendable to an arbitrary number of modules by adding to the length of the robot. This next set of locomotion gates combines simple modes to achieve more complex locomotion. In this case, segments are added perpendicularly, interspersed between the original segments. This gate may be used as a platform to carry objects. The more modules used, the larger and heavier the object may be. The next 2 gates will show the robot turning. In this gate, as the robot turns, the 2 feet of the robot in contact with the ground rotate with respect to each other, and so they must slide on the ground. This would create problems if the robot were trying to navigate using dead reckoning, or if it were walking on carpet. Here, segments are again interspersed perpendicularly between segments. Since the segments are placed on the ground at one end and picked up at the other, no sliding will occur. The following two gates are called exotic gates. While not necessarily efficient or useful, they are still interesting. This gate is called the moonwalk. Manipulation of large objects and locomotion can be considered equivalent. Here we are doing both. This last simulation is not a locomotion mode, but it shows one possible dynamic reconfiguration of polypod.
Cool. Well, the early realization were really difficult and very simple, but today there are a lot of interesting devices that can carry all these simulations, and I hope we will have the chance to see them later. Okay. So today we are going to start on instantaneous kinematics, and that is going to introduce the model I discussed many times before. I refer to this kinematics model called the Jacobian matrix. That is going to be a very important part of all what we're going to do later in terms of not only the motion, but also the dynamics of the motion. So you remember our first task was to try to understand how we localize the end effector. So we know now this frame at the end effector, and we can describe the position and orientation of that end effector with respect to a fixed frame. So if we start moving, we are going to have small displacement that we can monitor in time, and if we go to a small displacement from the current configuration. So we are at a given configuration, we have theta 1 to theta n, and we know the x position, but if we make a small displacement of theta, so that would be a sort of delta theta that we are introducing to each of those joint angles, we are going to have a small displacement delta x. It's not only delta x in the position, but also in the orientation. And the question is, what is this delta x, given that we know delta theta and we know the theta, where we are? So this question, finding the relationship between delta theta and delta x, is answered by a linear relationship that connects the two. Delta theta and delta x are connected by I cannot hear you, please. Derivatives. Yeah, it is derivatives. But what is this model that is going to connect the two? You guessed it now. So delta x is going to be related to delta theta by a matrix. Yeah, the Jacobian. So delta x, delta theta, or the derivative, if we divide by time, theta dot and x dot, will be related to each other through this Jacobian matrix. Now, x dot, again, involves two things. Remember, our representation of x involves the position and the orientation. So there is a part that discusses the linear velocity, and there is another part that represents the angular velocity in this vector. So what we need to do is to find this relationship and establish this Jacobian matrix that connects those displacements. So to study the Jacobian, we're going to start by looking at differential motion, and we're going to discuss how do we compute a linear velocity at a rigid object, how angular velocity are computed as we propagate, and how we can compute the impact of angular velocity on the linear and angular velocity of the end effector. So this will take place through this propagation of velocities from one joint to the next, and that is going to provide us with a sort of recursive relation that will allow us to find the velocities at the end effector. We are going to examine another way of doing this analysis, rather than propagating velocities, we're going to examine the structure of the kinematics of a robot and its impact on the end effector velocities. And that would lead us to something very interesting we call the explicit form of the Jacobian matrix. That is, we are going to analyze the kinematics, and we will see that in each of the column of these matrices, we are going to have an association with the joint, with a specific joint. So if we take the first column, this first column corresponds to the first joint, and its impact on the velocity at the end effector, velocity, linear and angular. So this explicit form is going to be very important in establishing the model that connect displacement or velocities at the joint and at the end effector. And this model is going to be very important also in establishing the relationship between forces. Forces are acting on the joints depending on the type of the joints. If we have a prismatic joint, we have a force. If we have a revolute joint, we will have a torque. Now, if we apply a set of torques to the arm, there will be some resulting forces at the end effector. It turned out that the relationship between torques and forces resulting at the end effector come from exactly the same model, from the same Jacobian. There is a dual relationship between velocities and static forces that we will use, and this will lead us to establishing the relationship between torques and forces. So first we are going to analyze those displacement, and what we need is a description of our generalized coordinates. So we picked the joint angles as generalized coordinates, but sometimes we have joint displacement if we have a prismatic joint. So what we will use a variable we call Q to represent, to capture the joint angle, whether it is a prismatic or a revolute joint. And this is done by saying that, by introducing Qi as theta I or di, epsilon is equal to 0 or 1. It's a binary number. So if we have a revolute joint, epsilon is 0. If we have a prismatic joint, it's 1. And epsilon bar is the complement. So the Qi is going to be either theta I or di following the type of the joint. So with the joint coordinate vector Q1, Q2, Q3, now we can go to the representation, find the relationship between the two, that is between X and Q, and then compute those differentiations. So we can differentiate, as you suggested, to compute this relationship. And this differentiation is going to involve multivariables. So X, Y, Z, whatever representation we have, maybe alpha, beta, gamma, and then Q, Q1, Q2, Q3. So this is sort of a vector differentiation. We have X1 that corresponds to the first function, F1. This could be just the coordinate X. X2 is Y, etc. And we have all these functions. So the Jacobian could be computed simply by this differentiation, partial differentiation. We can compute delta x1 as the partial derivative of f with respect to q1, and f1 is function of all the q's, so we would take the partial derivative with respect to all the q's, and that provides delta x1. Delta xm, in the same way, we take the last variable, last function, differentiate, and obtain the relationship. Now here we have a set of equations. How many equations we have? Can you count them? M. So we have M equations depending on how many variables? Number of joints. How many joints we have? N. So it is basically M equations that is expressed in function of all these variables and variables. So do you have another way to write this equation so that is like a little bit more compact? Because I'm not going to write this every time. And so we can put it in a matrix form where delta x1 to delta xm is a vector delta x, and delta q1 to delta qn is a vector delta q, and the relation between the two is this matrix. So do you see the first column of this matrix? How we transform a set of equations into a matrix vector form. So how do we do that? So do you see, first of all, what would be the first column? Come on. What is the first column? Where is it? So all the coefficients of Q1. So the first column is the partial derivative of F1 with respect to Q1 to partial derivative of Fm with respect to Q1. So basically this is the matrix. And this is precisely your Jacobian matrix, which is a matrix with m by n. It's m by n, and it's connecting the delta Qn, n of them, to your delta x. All right. So here is the Jacobian. But doing this computation is not simple. You have different kind of representations. There are different ways of expressing your position and orientation. And if you go and analyze this Jacobian, you are going to find yourself analyzing both the kinematics, the representation that you used, and it's very difficult to make sense of what is happening. So if we take an example, let's take an example. Where is the example? Oh, yeah. By the way, this writing, I'm writing here a connection between delta Q and delta X. It is exactly the same matrix that connect Q dot to X dot. Because we are doing this differentiation. If you take it with respect to the time, then Q dot is connected to X dot through the same matrix. So the element of this Jacobian is the partial derivative of the function I with respect to J. And here is the example. So it's a very simple example. 2 degrees of freedom with, in the plane, lengths L1 and L2. And our representation is going to be just X and Y. So what is X in this case? Okay, let's do the DH parameters and do the frame assignment and the propagation. Or maybe you can just give me X directly by looking at the figure. And this is finished. Oh, good. Good to know. I didn't ask for this. Okay, so what is X? You have theta 1 and theta 2. So X will be on this direction. So it will be the cosines. So it will be L1, come on, cosine theta 1 plus L2 cosine theta 1 plus theta 2. Right, because we are taking with the, and the signs will give you the y. So here is L1 cosine 1 plus L2 cosine 1 plus 2 and y. So in this case, to differentiate, it's very simple. The differentiation gives you this, and now you have your matrix. And you could see that the first row is minus y, the second row is just x. So the Jacobian in this case is quite simple, and this Jacobian gives you this relation. For small displacement delta theta, you can compute the corresponding displacement delta x, and for for velocities in joint space, you have velocities at the end effector. Actually, this matrix has been widely used to control the robot, because you can say, I'm here, I would like to move the end effector with little displacement. You can take that displacement and generate a trajectory and compute small displacement delta thetas. So you want to find the delta theta that correspond to your input delta x. You want to displace the end effector by a little bit. You compute the corresponding delta theta. So how do you do that? How do you extract delta theta from this equation? We take the inverse, and using the inverse of this matrix, we can compute a delta theta that corresponds to delta x. And then we can drive the robot this way. And many industrial robots are driven using the inverse of the Jacobian. So let's take another robot we examined and see how this extends, how the Jacobian becomes a little bit more complicated. So this is a 6 degree of freedom that involves one prismatic joint. And you remember the schematic of this robot, theta 1, theta 2, theta 3. Theta 3 actually is D3 and the last rotations. And we have this table of DH parameters providing us with the description of lengths with respect to previous ones. And using this, we computed x, y, z for the position, these invisible 3 first component. This color is really difficult, but this is x, y, and z. And what is this vector? So the direction cosines, this is the x-axis of the last frame, that is the axis attached to the end effector, expressed in the base frame. And the second set of ups. And this is the y-axis, and this is the z-axis. Okay, so let's differentiate. And okay, the first one is very simple. You differentiate the first one with respect to cosine to q1, you get minus y. You get sine 1, sine 2, d3 plus cosine 1, d2. And you differentiate with respect to q1, the last component, that is the z component, you get 0. So now I want you to give me the second column. So how do we find the second column of this Jacobian matrix? We differentiate x, y, z with respect to q2, right? So what this should be? Someone said cosine 1. I heard. No? Any volunteer to do the second column? So the first variable is x, which is it has a function of q2 in sine 2, right? So the derivative of sine 2, do you remember those derivatives? What is the derivative of sine 2? Cosine 2? So it will be the first cosine 1, cosine 2, d3, and that's it. The second component, sine 1, d, cosine 2, d, 3. And the last one, minus sine 2, d3. So that's correct? Okay. So what about the third column? We derive with respect to d3 or q3. This would be there is only one here, so louder. Uh-huh. And,
Sine 1, sine 2.
and cosine 2. Excellent. And with respect to Q4? Does X, Y, or Z depend on Q4? No, so it should be 0, 0, 0. Okay, well, here is the part of the Jacobian related to X dot, Y dot, and Z dot. That was easy. Yes?
What are the other joint coordinates for Q4 through 6 again?
Well, they are not, I mean, X, Y, and Z is independent. You remember because X, Y, and Z was chosen at the wrist point. So when we move the end effector, the point is still fixed. So you get 0 columns for 4, 5, and 6. Okay? All right. Well, what seems very simple for X, Y, and Z becomes a little bit more challenging for the orientation. So let's take R1, R2, R3. You remember R1, R2, R3 are these 3 vectors representing the direction cosines. And if we write the derivative, it's going to be R dot 1, R dot 2, R dot 3 would be related to the Q dots by the partial derivative of R1 with respect to Q1, first column, 2, etc. to 6. So let's do that. Okay, 5 minutes? Well, I doubt it. Well, I'm sure, I mean, you might be able to write a program to do it, in fact, and still it will be quite complicated to find all these columns. But more than that, what do we have here is we have a matrix that corresponds to this description, and which means that we are spending this time to compute a Jacobian for the position and the orientation represented with direction cosines. And this matrix will have dimensions of, we found the first one 3 by 6 and the second one 9 by 6. So it will be a 12 by 6 matrix. So if you look at the rank of that matrix, it's not square matrix. Its rank is at most 6. But you cannot really analyze this matrix and make sense of what is happening. You remember there might be configurations that can bring singularities if we are using Euler angles or some minimal representation, and that is going to be reflected in the Jacobian. So our Jacobian is really not giving us the properties of the mechanism in terms of the linear velocity and angular velocity. Rather, it is mixing everything up, mixing the representation properties with the properties of the mechanism itself. So when we have an XP and XR, as we saw, different representations for XP or for XR. We have Cartesian, spherical, cylindrical coordinate for the orientation. We might have Euler angles, fixed angles, direction cosines, Euler parameters. And if we compute the Jacobian this way, that is, if we compute the Jacobian for the position from differentiation and from the orientation, this resulting Jacobian is going to be depending on the representation. And it will have dimensions that accommodate the representation. So this is not something that you want to do. You are trying to find the Jacobian of your robot. You want to find the properties associated with the robot in terms of its linear velocities and angular velocities. So this is really what we are after. We are trying to find how the end effector moves when we put velocities at the joints, when we make small displacement at the joint. What is the linear velocity? What is the angular velocity? So the linear velocity and angular velocity will be related to q dot. And there is a matrix that provides that relationship. It is the Jacobian matrix that connect this 6 by 1 vector. Linear velocity is Vx, Vy, Vz. Angular velocity is omega x, omega y, omega z. And q dot has the number of degrees of freedom. And this Jacobian will be sort of like the basic Jacobian that is describing the kinematics independently of your representation. What is interesting is this Jacobian J0 will play a very important role in the kinematics, but also in describing the velocities for your representation. Any representation that you will have can be connected to this Jacobian because any representation of velocities can be connected to linear and angular velocities. These angular velocities are instantaneous. So there are representation of the orientation if we take three Euler angles, alpha, beta, gamma. If you take the derivative of those angles, alpha dot, beta dot, gamma dot, they are related to omega. They are not equal to omega. The derivative of Euler angles are not angular velocities, but they are related to the angular velocities by a representation, by a very simple model, a 3 by 3 matrix. And using those relationships, we will be able to describe the Jacobian for any representation and connect it to this Jacobian. So if we have spherical coordinates, the derivative of the spherical coordinate are connected to the linear velocity by a simple matrix that is only function of the representation of spherical coordinates. If we have Euler angles, we connect them to omega simply by a 3 by 3 matrix that only involve alpha, beta, and gamma. So through this relation, we can see that we can connect x dot for the position and orientation to v omega. And because v omega is connected to q dot, then we can have a relationship between the Jacobian associated with this representation and the Jacobian associated with the kinematics. So here are some examples. If we take Euler angles, so if we take alpha, beta, gamma and take the derivative, we can see that these derivatives of alpha, beta, gamma are related to omega by a matrix, which is in this case the sine of alpha, cosine of beta. So it is only function of Euler angles. If we take Cartesian coordinates, the matrix that connect Cartesian coordinates to linear velocity is simply the identity matrix, because the derivative of Cartesian coordinates are the linear velocities. So using this step of computing the linear and angular velocities, we will be able to generalize and find the Jacobian associated with any representation. So the Jacobian for a representation x is xp and xr, will be a Jacobian we call jx for that specific x. And this Jacobian will be related to the basic Jacobian by a matrix E, where E is going to connect the descriptions of linear and angular representation to v and omega through this relation. So here is an example. If we take x dot as related to v through this matrix, and x dot are related to omega through this matrix, because v and omega are related to q dot by j, v and j omega, then we will have this relation which leads to this relation, that is the part associated with the position representation is simply the Jacobian v associated with linear velocity pre-multiplied by EP, that is the which is function only of the representation, or ER for the rotations. Which means if we combine them together, we obtain this relation that is the Jacobian associated with a representation is related to the basic Jacobian by an E matrix that has a diagonal form where EP is the matrix associated with the linear motion and ER is the matrix associated with your representation of the rotations. So if we select Cartesian coordinates, EP will be what? Identity matrix. So if we have always Cartesian coordinate, we have only to worry about ER. Okay, you get this point? So now the focus is on J0. We have to find J0, linear and instantaneous angular velocities. But first, let's examine some E's. For the position representation, X, Y, and Z, we said is the identity matrix. How about cylindrical coordinates? Cylindrical coordinates, you get rho, theta, and Z. And here is the relationship between X, Y, and Z and those coordinates. All what you need to do is to relate the differential relationship between delta X, delta Y, delta Z, and those coordinates, and you find the matrix. And that leads to this matrix for cylindrical coordinates. What is nice is, you go and store this in your library and you have access to all these. You don't have to recompute them. So for cylindrical coordinate, you have this matrix. For spherical coordinates, you have this matrix. So these are things just are there. If you want to change your representation, you just change your EP. Now, for the Euler angles, we saw that we have another relation that is this 3 by 3 matrix. Anything special about this matrix you notice? Anything bad about this matrix? No? It's fine? Yeah?
Problem is sine beta is equal to 0.
Very good. You remember what happened when we had sine beta equal to 0 before? We had a singularity of the representation. It appears again in the velocities. So when you get to that location, you have a problem because every time beta is equal to some integer times pi, you have a problem. And that is the problem with Euler angle representation or any minimal representation. You get a singularity in your representation that is going to lead to a singularity in your Jacobian associated with that representation. Okay, so we have established this relation that we should not worry about the representation. We will find E for each of the representation. There is no problem. All what we need is to find and establish this relation between V omega and our Q dots. So from now on, I remove the 0. The basic Jacobian is the Jacobian. When we say Jacobian, it is J, and this Jacobian is relating the Q dots to your linear and angular velocities. And our task is to find V and omega as a function of all these Q dots. Okay? So let's do that. I'm almost certain all of you understand what is the vector of linear velocity, but probably there is some confusion when we start propagating and moving and putting multiple rigid bodies and multiple frames. So I'm going to go a little bit back and describe how we can compute linear velocities as we propagate our vectors and we go from one link to the next. So here is a point and this point is moving with respect to something. If it is moving with respect to the origin of frame A, we talk about the velocity, p of that point with respect to A being the frame. Now, you have to distinguish between this magnitude of the velocity and its direction as a vector and its components and where we are expressing this vector. So this vector could be expressed in frame A, right? We can have its component in frame A. But also we can express it in frame B, and we can have its component in frame B. But still, this vector is the vector representing the velocity of point P moving with respect to frame A. Now, if you want, we can put it in C. So don't be confused about the vector and where we are expressing this vector. And that's why I'm putting P/A specifically to show that I'm measuring the magnitude of the velocity, the vector of velocity, with respect to frame A. Now, let's have the following situation. I have this point that is moving with respect to frame A, so I have a vector representing the velocity of point P with respect to frame A, this vector. Now, if frame A is moving with respect to another frame, and this is the case of link 3 moving with respect to link 2 or whatever, there is a velocity of the origin. And if this velocity is the velocity of the origin representing the velocity with respect to frame B, the question is, what is the velocity of P with respect to frame B? What would be that velocity? Obviously, it's going to be the sum of the velocity with respect to frame A and the velocity of the origin with respect to frame B. So you just add these two vectors, and that is the velocity of the point P with respect to frame B. So here we discussed the motion of the frame A with respect to B, and this motion is uniquely produced by a translation with a velocity VA of the origin of that frame with respect to B. Now, it becomes a little more complicated when you have a rotation. So suppose you are translating and at the same time you are rotating. So we need to introduce the effect of rotation. And when we rotate a frame, different points will move at different velocities, right? So if you're rotating an object, depending on the axis of rotation, this point is moving faster than this point, if I'm rotating about this axis. Actually, on this object, there will be point that will have zero velocity. Do you know which points will have zero velocity? The points that lies on the axis of rotation. So if we take an apple and we rotate it about this axis, there will be some points that will not be rotating, but actually the points on the outside will be rotating more. And what we are concerned with is if I have a vector of instantaneous velocity, what are the linear velocities at different points located by a vector P? And that is the question we need to answer first. Do you know the answer? Not yet? 3-4 minutes, you will know the answer. Okay, so we have an axis of rotation. We have all these fixed points. So we're just doing a pure rotation. So these points are fixed. And let's have a schematic simpler to see. So obviously the points closer to the axis are going to move at slower velocities. Let's pick a point P. and we're concerned with the velocity at this point. The angular velocity measured about this axis is omega, and omega itself is representing the vector. So it's vector and magnitude. Now, what is the magnitude of Vp and its value, given that we know its location P and we know omega? Well, first of all, we need sort of like we need to locate P with respect to some frame. And we need to make sure that this frame is not moving. So we put a frame on the axis. So the origin of the frame is fixed with respect to this rotation. And we locate it with a vector P. Okay, now we have everything we need to find Vp. So let's see. The magnitude of Vp is going to increase with the magnitude of omega. That makes sense. It's going to increase with the distance from the center, which is the vector P multiplied by the sine of the angle phi between the two axes, right? The further away from the center, the largest the Vp is going to be. And we can notice also that Vp is orthogonal to both omega, the axis of rotation, so the velocity is orthogonal to that, and also orthogonal to the location, the vector locating that point, because we are taking the point from the fixed point. So that means, with all of these, that means what? Vp is equal to, when you have like three vectors that are orthogonal and you have the sign, then you will have cross what? Product between the two. Which one is first? So Vp is equal to cross product of what by what? Well, you have two choices. I said you will know in 4 minutes, and it is almost 4 minutes, so here is the answer. Where is the answer? Here. So it's omega cross P. It's not P cross omega. By the way, we will see P cross F to produce the torque. There is a dual relation. So here we have velocity, you have omega, you have the point. Now you can imagine on the same figure that instead of omega I'm applying a torque, and the result will be a force. And there is a similar relationship between the two. And in that case the relationship will be involving the distance first times the force and to produce the torque. Okay, we will see that later, probably on Monday. So now we have this relation. Linear velocity is the angular velocity across the distance. It is represented as a vector model here. What we need to do in order to go to the matrices, we need to introduce a matrix representation. That is, instead of writing a vector representation, I need to write this in a matrix form. So how can we, so B is a vector now, and C is a vector, and A is the vector transformed into this matrix operator that does for you the A cross B. So we need to find this A hat, the operator that is equivalent to A cross. Are you familiar with this? The cross product operator? So this is essentially a skew matrix, a skew symmetric matrix whose diagonals are 0, and which is formed directly from the vector A, Ax minus Y, Z component, and it is non-symmetric matrix. And you start with a vector A. If you take this vector and put it in this matrix, then you get the matrix that will operate on the vector to produce the cross product of that vector, and that will be your resulting linear velocity in the case of omega cross p. Okay, so we represent a hat as this operator. All right, so in our case, Vp is omega hat cross the vector p. And omega is this matrix. So this is something you might need to remember and just write down and put it somewhere in your notes. Okay, let's use it. So now that we are going to combine linear and angular motion, the new velocity there in that frame is going to involve this omega cross p, and this will be added to that vector. That is, you have the velocity of the point coming from the linear motion, the velocity of the origin, and the velocity due to this rotation. And this is omega cross the vector locating the point. Now be careful about where you express your vectors, because if we say we are going to compute those quantities to express them in frame A, the result has to be expressed of each term should be expressed in frame A. So if we have the vector P expressed in frame B, we have to transform it to frame A and then do the multiplication, and we have to express this in frame A so that the whole result is finally in frame A. So you have to make sure that each term or each vector is expressed in the same frame. It doesn't matter which frame it is, but it has to be in the same frame. And if you need A, then everything has to be transformed to A. Wow, we went fast. Good. All right. We're ready now. So we're going to take those concepts and now apply them to our mechanism. And I think we're going to skip the movie segment. We will see it on Monday. So the way we're going to proceed is by taking those velocities from one frame and taking those velocities and propagating them as we move from one link to the other until reaching the velocity at v and omega. So this propagation is going to involve two velocities, the linear velocity v and the angular velocity omega. All right. And when we get there, we will have the Jacobian that will be in the total velocities. That is, once you reach v and omega, you will have implicitly the expression of the Jacobian multiplied by theta, which you can extract. So let's start with the linear velocity. So here, let's take a vector vi and omega I that is describing the velocities of this origin of frame I and the rotation of the frame with respect to omega I, that is representing the instantaneous velocity. And let's go to the next frame where we have a new velocity, linear velocity I plus 1, and the new instantaneous angular velocity omega I plus 1. So what is the resulting linear velocity vi plus 1 as related to the velocity vi? So first of all, don't look at your notes and let's see if you have the intuition about it. So what would be vi plus 1 as a function of vi? Is it smaller, larger? So Vi plus 1 is going to be equal to come on. Is it related to Vi by any chance? So there is a translation. Everything is moving with Vi. So the Vi plus 1 is going to have Vi in there, without doubt. But there are two terms that will appear. And the first one is omega I cross Pi plus 1. You didn't tell me why, but maybe now I'm showing you what is the term. Tell me why. Yes?
Well, any movement in this frame is going to add to the linear velocity in that one.
So the linear velocity is computed at the origin of that frame, right? So the omega involved will not be that omega I plus 1, the large omega I plus 1, this instantaneous rotation here. If this is a revolute joint, this will be rotating. So this rotation will not change the velocity here. What will change the velocity here is the rotation omega I of this point located by this vector. So this would be omega I, which is here, cross this vector locating this point. So this is the first term. Now, anyone can explain the second term? Yes?
For prismatic joints?
So the second term only appears if that joint, the z-axis, was not a revolute joint, but was a prismatic joint that is translating along the z-axis, so along zi plus 1, and the magnitude will be the d dot I plus 1. D is a variable in this case for the prismatic joint. So this is the d dot I plus 1, zi plus 1 is the local velocity in frame I plus 1 of that point, and the omega I cross Pi is the contribution of the rotation of the frame and plus all the translation that were happening before. You had a question?
Oh, yeah. It looks like the prismatic is on the Zi in that
Yeah,
frame.
it is always on the Zi plus 1. So this will appear only if this was not revolute, it was prismatic, and it is translating along the Zi plus 1.
Oh, I just assumed because I saw the two-headed arrow over in frame.
I'm not representing d dot here.
Okay.
Okay, now what about angular velocities? We are concerned with what is omega I plus 1 as a function of omega I. So if the joint I plus 1 was prismatic, so there is no rotation between the two, what would be omega I plus 1? It will be identical to omega I. If it is revolute, then there will be the omega I plus 1 that will be added. And omega I plus 1 is simply the dot of theta I plus 1 along Zi plus 1. So to propagate from one frame to the next, what we need to do is to take these two relations and go from the base, the fixed base, where V0 is 0, it's attached to the ground, and omega 0 is 0, there is no motion, and propagate to the end. And when we reach the end, we are going to have the V associated with the end effector, the omega associated with the end effector. Now, in those relations, what do you see? You see that you are using d dot and theta dot, and the kinematics, obviously, the z-axis. So that means we are going to be able to compute the total velocities v and omega at the end effector as a function of the theta dots and the d dots, all the q dots. Yes?
Are these two frames rotating independently? Like, is there a revolute joint on I, and is there a revolute joint in I plus 1?
There is a revolute there could be a revolute joint in a frame omega in I plus 1 or a prismatic joint. And depending on the nature of the joint, you get either d dot or you get the omega I. Okay? So when you do this computation, you are going to have an expression of the total linear velocities, total angular velocities as a function of the d dots or the theta dots. So for joint 1, v1 and omega 1 can be expressed in frame 1, and this is going to be sort of using this relation to compute the omega I plus 1 from the initial frame. This would be the expression for I plus 1, and this will takes us, because we are expressing all these in the frame I plus 1, we are going to find the total expression of the velocities in the frame n as we propagate. And once you reach the total final velocities in frame n, you can transform them back to the base frame, and that will give you the total velocities at the end effector in frame 0. Yes?
In your previous slide, where did you get the theta I plus 1 from?
Theta?
The previous slide.
Yes. Which variable?
Theta, omega I plus 1 equals to theta I plus 1. Where do you get that theta I plus 1 from?
This one? Okay. So omega I plus 1 is the angular velocity associated with the motion of joint I plus 1, if the joint is revolute. And if the joint is revolute, the velocity vector is about the vector zi plus 1. So this is a unit vector, and the magnitude of that velocity is proportional to theta dot I plus 1. So this is actually joint I plus 1. If you take the derivative, you remember we aligned the rotations of each revolute joint along the z-axis. So that is where it comes from. Yes?
Theta I plus 1 and di plus 1, aren't those defined with, along the zi plus
Always.
1 axis? So it's
Yeah.
not necessary to have the dot product, right?
What do you mean it's not dot product?
Dot zi plus 1, that's not adding anything, is it? If they're
This point, this dot? No, this is proportional. It is not dot product. It is proportional. No, theta dot is a scalar, and the zi is a vector. So no, this is not a dot product. This is just a scalar multiplication. All right. Other questions? Yes.
Why is everything expressed in terms of the coordinates for I plus 1 if when you do the forward kinematics, you're going to get the inverse?
Okay, so the algorithm that we are using here for the propagation is taking the velocities and propagating to the end, so we compute that in frame n, and at the end, if we need them in frame 0, we do the transformation back to frame 0. This is the way this algorithm is done. You can do the computation backward, and you compute everything in frame 0. Or you actually, the most efficient place to do this computation, you know where? Not at frame 0 or at frame n, it is in the middle. Because those transformations becomes more and more complicated if you go from the base to the end. In the middle, the transformations are simpler. So if you transform just to the middle as you propagate, you will get the most efficient form. But in this algorithm, we are showing that if we use I plus 1, we will end up with velocities omega n and Vn that will give us the total linear and angular velocity in frame n. And if we need them in frame n, that is fine. Otherwise, we transform them here. Now, where is the Jacobian in all of this? Anyone can see the Jacobian? I showed you this recursive propagation. We forward propagation, computing the velocities, but where is the Jacobian? No? You cannot see it. Well, it is there. Have to find it, like you have to go inside. So you write out the relationships, you do the propagation. What do you need to extract from those expressions to find the Jacobian? You need to get the theta dot I plus 1 and the d dot I plus 1 out, and everything else is going to give you these columns of the Jacobian. So you cannot really see it, but it is there. Now, velocity propagation is really nice numerically, but it doesn't give you any idea about the structure, about the contribution of the joint, about your kinematics. And it is not really the best way to analyze your mechanism. What we're going to do, we're going to, in fact, analyze and work with this explicit form of the Jacobian that would allow us to really look at the mechanism and see immediately the Jacobian matrix and its columns and its structure. So next time when we analyze the explicit Jacobian, you will be able immediately to look at the mechanism. So now you see the Stanford-Scheinman arm. You look at Stanford-Scheinman arm and you see this is the first column, this is the second column, this is the third column. This is how the Jacobian is going to be. Before we leave, we still have a few more minutes. Just, there is an example. This example is useful if you want really to understand a little better the velocity propagation. And this example is done over a very simple 3 degree of freedom mechanism. We know the answer of the Jacobian. You know the Jacobian for this is, you write theta 1, theta, you can write x, y, and z, which is L1 cosine theta 1 plus L2 cosine 1 and 2 and L3 cosine 1, 2, 3, and sine, and you do the differentiation and you find your Jacobian. At the same time, if you do it through velocity propagation, using these relations, you go to the first propagation, the base is at 0, you compute the linear velocity at P2, you compute it, you get this expression, you compute the velocity of 2. So just take a look at this example, and once you completed the propagation, you find that your omega vector is the sum of these velocities, which means essentially your total omega is coming from these 3 rotations, 1, 2, and 3 contributes to the total rotations of your end effector, and the linear velocities are going to be, this would be the Jacobian. So if we extract theta dot 1, theta dot 2 out, this is your Jacobian for the position, and this is your omega, so this is the Jacobian for the omega. Now, this whole computation turned out to be, well, through this numerical propagation, but if you do it through the analysis, what you're going to find is, for j omega, you see here, what do we have? 0, 0, 1. 0, 0, 1, 0, 0, 1. What is this 0, 0, 1? This is the z vector. All the omegas are rotating about the z vector, which means essentially the Jacobian associated with angular motion is simply the zi vectors associated with the joint angles. What is this? Well, I mean, this could be directly computed from the partial derivatives, or it could be computed from this cross product of those joint angle rotations with the point locating that point. So we will see that structure next time, and then you can see much better the properties of the Jacobian as relates to the kinematics of the robot. I will see you on Monday.